All right, so we're talking improper integrals. So improper integrals, if we recall, are any integral that involves an infinite limit in it in some way, or it has an infinite discontinuity with it. Everybody good with that? Good with that at home? I can see the people here nodding their heads. So
yeah.
All right. So let's do an integral like, let's do the integral from 1 to infinity. We're going to start with 1 over x dx. We're going to do a couple of different ones of these just to kind of sort of refresh our memory about how these work and sort of see some interesting results and see if we can recall it. So if we want to do the integral from 1 to infinity of 1 over x dx, first thing we have to do is we have to rewrite it as a limit. So this will become the limit, and then we can take any constants up here. We'll say a, limit of a approaches infinity of now an integral from 1 to a of 1 over x dx. And I know it seems sort of pointless to rewrite it as a limit, but the limits of a integral have to be real values, and infinity is not a real value. And so if you don't rewrite it as 1 to a or b to 7 or whatever it might be on the AP test, they're not going to give you the points for doing it. So just make sure you do rewrite it as a limit. So this should become then the limit of a approaches infinity, and then the integral of 1 over x should be natural log absolute value x. And we'll evaluate from 1 to a, and when we get the limit, a approaches infinity of natural log a minus natural log 1. Since a is going towards infinity, we can drop the absolute value on it because we know it's positive. Since 1 is positive, we can drop the absolute value on it. And we end up with natural log of infinity minus 0. And that should be infinite. This is infinity. And so we'll then say that this integral diverges. Good or no? Everybody here is good with that? Everybody at home is good with that?
Yep.
Wonderful. Okay, now we're going to do another one. We're going to do the integral from 1 to infinity of 1 over x squared dx. You guys want to do this on your own? Yeah? Okay. I'll give you guys like 30 seconds here to do this one on your own, or a minute or something. Well, I'll bounce the lacrosse ball that I take out of my drawer. That won't be a distraction to anybody here. Sorry, Jen. For those of you that work quickly, this is the next one we're going to do. Go ahead and do that one also if you feel like it. In fact, everybody do both of those. I'll give you an extra minute or so here. Now it's recording. Look at the problems. We did them. The first one came out to be 1 and the second one diverged. Cool. Hopefully that's helpful for the one person that's not here in class today and is not paying attention and learning the stuff they're supposed to learn. Okay. These we would know are of a form that looks like this. Integrals from 1 to infinity of 1 over x to some power. True? Right? We had 1 over x to the first, we had 1 over x to the second, we had 1 over x to the 1/2. Can somebody remind me? I don't remember. Did we prove for what values of p this integral will converge or diverge? We did not. Okay, cool. So we're not going to do that right now. I'm going to tell you right now what they are. We're going to prove it when we start doing series because it becomes a very important result when we're working with series. These become, we're going to write series that are represented using this integral that we will call p series. P there on the power of the x. So if x is less than or equal to 1, sorry, p is less than 1. p is less than or equal to 1, this diverges. If p is greater than 1, it's converges. You will be able to get a finite value for that. So that's something that's going to come up often when we talk about series. And we're going to look at these series of 1 over x to the p. And this will still hold true because of a very interesting and cool test called the integral test that we'll use. So just something to know. But also, if you just get something in the multiple choice that's like, oh, an integral from 1 to infinity of 1 over, the cube root of x, and multiple choice, you just know that it's divergent. You don't even have to think about it. Good? You guys good here? You all good at home with that?
Yes.
Yeah, if it's free response, you'd still have to show. Okay, so but there's two things. If it's an integral, if they give you the integral, if there was a free response and they said, what's the integral from 1 to infinity of 1 over the cube root of x? Yeah, you got to show it. Or 1 over x to the third or whatever, you got to show it. But if it was in terms of a series, you will be able to just say that it is known that this converges or known that this diverges by this test that we're going to talk about called the p-series test. So, depends on what form. Yeah. All good? All good? Everybody good? Good at home?
Good.
Yeah.
All right. We also might have improper integrals that look like this. The integral from 1 to 2 of 1 over x minus 2 dx. Yeah? What makes this an improper integral? It has an infinite discontinuity at x equals 2. So we will need to rewrite this as a limit as x approaches 2. And since our integral is from 1 to 2, we're approaching 2 from which side? Should be from the left. So limit as it should be not. Let's call it b. We've been using a. We'll use b. We've gone through the alphabet. Okay. Limit as b approaches 2 from the left of the integral from 1 to b of 1 over x minus 2 dx. And this again becomes pretty straightforward. All we have to do is integrate it and then evaluate it. So this becomes the limit as b approaches 2 from the left of natural log out to the value x minus 2, all evaluated from 1 to b. And we'll write that out as the limit as b approaches 2 from the left of the natural log of b minus 2 minus the natural log of 1 minus 2. And the second part of that there becomes natural log of 1. I forgot I can use my finger to write on the board. That's exciting. Why am I using this stupid pen? Yeah. This becomes natural log of 2 from the left. This thing right here, what does it become? Natural log of b minus 2. Should go towards negative infinity. And then this becomes 0. So we'll say that this diverges. Good or no? You okay, Noah? Yes. Okay. Good? Good? Good?
Yeah.
Very good. People at home are good?
Yeah.
Okay. I'm going to give you guys one more to do. Let's do an integral. Let's do the integral from 1 to 3 of 1 over x squared minus 6x plus 8. Let's do that. I think you guys should be able to do that one on your own. What do you guys think? Yeah? All right. It probably will take you a couple of minutes, so I'll give you like 2 or 3 minutes to work through. Those of you that are here in class, remind me to read. Okay. Now, first thing we need to do is recognize that this should factor in the denominator to x minus 2 and x minus 4. And then we'll say, okay, if we're looking at an integral from 1 to 3, this has an infinite discontinuity of 2, which is on that integral. The infinite discontinuity of 4 doesn't matter. So we're just going to worry about 1 and 2. So we need to separate this into 2 different integrals to start with. Y'all good with that here? Yeah, everybody good? Separating into 2 integrals. So 1 would be the integral from 1. In fact, let's make our lines a little easier here. I think I got this figured out. I'm not too close up here. The limit as a approaches 2 from the left of the integral from 1 to a of 1 over x minus 2 times x minus 4. Plus the integral, the limit again, plus the limit as b approaches 2 from the right of the integral from b to 3 of 1 over x minus 2 times x minus 4. Yeah, and then how do we have to do that integral? Each of those integrals has to be done using a partial fraction decomposition. So we're going to say 1 over x minus 2 times x minus 4 is equal to a over x minus 2 plus b over x minus 4. We're going to multiply the a by x minus 4 and the b by x minus 2. We'll do the numerator and the denominator. So this will give us 1 is equal to ax minus 4a plus bx minus 2b. Everybody here good with that? Y'all good with that at home?
Yes.
All right. Then we can solve our system. So we have 0 x's and a plus b. So a plus b is 0. And over here we've got 1 is equal to negative 4a minus 2b. However we want to do, we can solve this system of equations. So we can make a equal to negative b. Just replace all the a's with negative b's. So that'll give us 1 is equal to a is negative b. That becomes 4b minus 2b. So 1 is 2b. B is a half, which gives us a is negative a half. That y'all got for your partial fractions? B is a half, a is negative a half. At home, you guys good with that?
Yeah.
Yeah.
Yeah. So then we're going to rewrite this as a limit as a approaches 2 from the left of the integral from 1 to a. No, I forgot what was it. Well, yeah, but like that. What was my a and my b value for? What should I be writing?
It is negative 1/2, so negative 1. Well, you can take the 1/2.
Oh, no. Was it x minus 2 or without the x minus 4? That's x minus 2. Plus 1 over 2 times x minus 4. And then x plus the limit as b approaches 2 from the right of the integral from b to 3 of that same thing. And there's a dx at the end that I'll have room for. Okay, good? Everybody good? Okay. So we can take the 1/2 out if we want, or we can just integrate. It doesn't really matter. I guess we can integrate. Let's integrate. So we've now got the limit as a approaches 2 from the left. If we integrate negative 1/2 of x minus 2, that's just negative 1/2 of the natural log absolute value x minus 2 plus 1/2 the natural log of the absolute value of x minus 4. Do that from 1 to a. And then we've got the limit as b approaches 2 from the right. And this is going to be the same integral, negative 1/2 natural log absolute value x minus 2 plus 1/2 natural log absolute value x minus 4. And that's all going to be from b to 3. So far, everybody good? Everybody here good? Everybody at home good?
Good.
Great. All right. Now, we should be able to, like we were saying, we can take the 1/2 out of all of that for each of those. And then we should be able to combine the logarithms within it together. So we should be able to make this 1/2 of the limit as a approaches 2 from the left of the natural log of the absolute value. This one is a positive x minus 4. This is a minus in front of it. So we'll do x minus 4 over x minus 2 for the first half. Everybody good with that? At home, you good with that? Good. Everyone good?
Good.
Plus, and then we're going to have another 1/2, and we're going to have a limit as b approaches 2 from the right. So we're going to have natural log absolute value x minus 4 over x minus 2, and I should probably write the values that we're going for. 1 to a, and this one is b to a. Okay. Good? Good. All right, so now we've got 1/2. Limit a approaches 2 from the left, and this is natural log absolute value a minus 4 over a minus 2 minus natural log absolute value of -3 over -1 plus 1/2 limit b approaches 2 from the right, natural log absolute value of -1 over 1 minus natural log absolute value b minus 4 over b minus 2. Good? Okay. Everybody good at home with that?
Good.
Okay. As a approaches 2 from the left here, what do we end up with for this limit? We end up with -2 over 0, which becomes -2 over infinity, which becomes natural log of 0. Right? And so if it's natural log of 0, that should become be a negative infinity. We're approaching 0 from we're coming from the right hand side because it's all x to the right. So this becomes negative infinity. And as soon as we get a negative infinity in there, we can just go straight through and say that the entire thing backwards. Don't have to worry about evaluating. So, yeah, good with that here? Everybody at home good with that?
Pretty good.
Pretty good? Conceptually okay? A lot of work? Or no really?
Yep.
That's what at the end I was like, I don't know if I'm done.
Yeah, it's a lot of work and you get it divergent. But you learned a lot about it, right? You learned that there's an infinite amount of area between them. Yeah, really good. All right, we're all good? Everybody's good? Okay.
I had a question, like, for like, if when we get something like this on the test, then like how fast would we necessarily be expected to solve something like this in like a timed situation?
If they give you this question, and they would not give you this question in the multiple choice. There are, on occasion, they will give you some improper integrals in the free response. This is probably a little more time consuming than what they would give you. I would expect that, they might give you this same integral, but having it be like from 1 to 2 or something like that, rather than 1 to 3. So you don't have to separate it into 2 integrals. And that would be one part of probably a 3-part free response question. So 4 to 5 minutes to do something a little easier than this.
Gotcha. Okay.
Does that help?
Yep.
Yeah. And by the middle of next week, actually probably before then, by the beginning of next week, I'm going to start talking about some of the non-series free response questions while we're still covering series, just to start so you guys can see what you might expect, especially with like BC only material in terms of what the free response questions will look like. So I'll start posting those up. I'll probably post them up on Friday actually, so you guys can start looking up the weekend. Hopefully that will help. Good? Yep. That's kind of, we got 3 weeks. Those of you taking the May 4th test, you got 3 weeks. Say you? No, you? One of you, not you. And a couple of you at home, right? You got 3 weeks till that AP test, so we're gonna fly through it. What? Are you allowed to still? Yeah, if you can, I might as well. Anybody have any questions on any improper integral stuff? Any of the review stuff that we've done in the last 2 days? People here, you're all good? Or just anything else you want me to talk about in review? No? People at home? Any questions on anything we've reviewed or anything else that you'd like me to quickly review before we move into our new stuff?
All good?
All good? All
I
right.
have one question.
Oh, you have a question? Yeah.
Like on one of the improper integral problems a few slides ago, I think you had like a limit as one approaches a of the integral from 1 to a of 1 over x squared dx. And you changed that to the limit as a approaches infinity of negative 1 over x. Can you explain how you got from 1 over x squared to negative 1 over x?
That's just the integral of 1 over x squared. Right?
Oh wait, I forgot the integral. Okay, I'm sorry, I'm dumb.
What?
Oh, I forgot there was an integral sign there. Sorry, I'm dumb.
This is the power rule of the negative 1 divided by negative 1.
Yeah, sorry.
Okay, that's fine. Everybody good now? Any other questions? Did you guys hear this question? Yeah. You guys can hear him? Okay, it's just so quiet. Anybody else? Any other questions? We're all good? All right. So we're going to pick up back where we left off. We were talking about differential equations. We had done some separable differential equations, some basic separable differential equations, where we had to separate the variables, separate x and y, and integrate. We did some where it was like even easier than that. We didn't have to separate the variables. And then we were looking at some equations that we may not be able to, some differential equations that we might not have been able to solve, and we sketched some slope fields. You guys all remember sketching slope fields? Yeah, to just get a graphical representation of what the solution might look like. So we're going to pick up there with something called Euler's method. Euler's method is just a way to approximate the value of a function at some specific point, given its differential equation. So rather than the slope field, which lets us sketch the full curve, this will help us to find the approximate value of the function. Let's say I have the value at x equals 1, and I want to know the value at x equals 2. We can use Euler's method to approximate it just given the differential equation. Okay. So that's what it's going to do. And it's going to use the idea of linearization. And so linearization, where we take the tangent line and we use that to sort of make a good approximation on a small interval, and then we're going to use that. So what we're going to do, let's suppose, let's suppose we know this value right here for our function. And let's say that we want to approximate, that's 1. Let's say we want to approximate the value of 2. Well, we're going to say that the tangent line at 1 looks about like this. And then the tangent line at 1.2 looks about like this. And then at 1.4 looks like this. And at 1.6 it looks like this. And 1.8 it looks like this. And at that gets us to 2. If we do the tangent line at 1 point, we're just going to do a bunch of little tangent lines rather than sketching a curve through. But we're going to do a bunch of little tiny tangent lines on small intervals to approximate what that function and how the function behaves at that point to get us to the point that we're looking at. That wasn't a very good picture. So those of you that wrote down that picture, you wasted your time. That was a bad picture because I can't draw. But we're going to just basically, instead of it looking like a smooth curve, we're going to make it look like, all these little tangent lines to get this value rather than this value that we started. Does that sort of make sense? We're just going to use little pieces of tangent lines as we go along that model what the curve looks like on a small scale to find out what the value of the function is close to where we're looking. So we'll have to have an initial condition in order to do this. Then we're going to use our differential equation to find the slope at that point. Once we find the slope at that point, we're going to take that and increase our x by a little bit. multiply that x increase by the slope to see how much y changes, and that will give us a new point. And then we will repeat that process with the new point. And then we will, find the slope at that new point, move over a little bit with the x, figure out how much that makes the y value move, and then get a new point. And then we'll do that again, and again, and again, until we get, until we get to whatever value we're looking. We may start at 1 and go to 2. We may start at 3 and go back to -2, or 3 and go back to -2.5. On the AP test, they will always tell you how many different increments they want you to use. So we'll probably do like 5 here, just to like get a good approximation. Generally on the AP test though, because you're short on time, they will only ask you to do like 2 different increments. You won't get as good or an accurate of an answer. But we're just going to do like 4 or 5 for each one, just to get the idea of the process that we will be using. And then you'll only have to use that process a couple of times on the AP test. My guess is you will see Euler's method either once in the multiple choice, but more likely once in the free response as part of a differential equation question where you also might have to solve a separable differential equation problem. But it varies on where they put it. So, does that the idea, the concept sort of makes sense of what we're going to do? Y'all good here conceptually understanding what we're going to do? At home, are you good?
Yep.
Yeah? Okay. Y'all, people still writing this down? Yeah. Exactly. Okay. You could use it for any differential equation to approximate it, but generally, I mean, what's the point? Yeah, it just requires. Then you could find the exact value. Generally, they will. Then on the AP test, they may say use Euler's method to approximate the value, even if you could separate it and solve it. Okay. But they might not. They may give you one, and you'll see the ones we're going to get are going to be like x plus 2y or something like that. Ones where we can't separate the variables. Normally, it's x times 2y we can separate variables, but x plus 2y. I don't know if you guys could hear Noah's question there at home. He was asking, I forgot what he asked, but you heard what I said. Y'all good?
Yes.
Okay. Derek, you still writing this down, or are you good? All right. You guys still writing down stuff at home, or are you good?
Good.
Good. All right. So we're going to just start here with this one. We're going to start with the differential equation x plus y, and we know that if we plug in x equals 2, we get 0. And so we want to use a step with delta x, or change in x being 0.2 every time. We're going to approximate the value of f of 3. So what I'm going to do, and you don't need to do this if you don't want to, but I think it's sometimes helpful. I'm just going to write out like a big old chart here with my initial coordinates. So I'm going to start out with my initial coordinates. I'm going to find the value of dy dx. Sometimes I think it is helpful then to just every time write your delta x and then your delta y, which will always be delta x times dy dx. And then from there, you're going to end up with a new point. So you're going to take your x and your y to find your dy dx. You're going to write out your delta x every time as 0.2. Use that every time to find your delta y. And once you have your delta x and your delta y, you'll just add those to your original point and put them down in your new point. Does that make sense to everybody? So we'll go through and do it together. So starting off with the first point, what's the first point we're going to use? 2, 0. Okay. So if xy is 2, 0, what is dy dx? Should just be 2, should just be x plus 1. And if dy dx is 2 and delta x is 0.2, what is our delta y going to be? should just be 0.4, right? It should just be the next two multiplied together, and the previous two multiplied together. So our new point will be the point x plus delta x, which is 2.2, and y plus delta y, which is 0.4. Everybody good with that? And sometimes I'll write that point down there at the end also, which is again, I column there, but you don't need it. Everybody good there? Okay, so then what is dy dx now at x equals 2.2? Should be 2.6, right? And we're going to multiply that by 0.2, which ought to give us 0.52. Yeah. Everybody go with that? And then we will add our 0.2 to our x, which is now giving us 2.4. And we'll add our 0.52 to our 0.4, which is now going to be 0.92. And we'll see that the arithmetic gets a little bit irritating pretty quickly, which is why on the AP test, they'll usually only have you do a couple of steps. Just for the practice, we'll do the bigger one. So what's our next dy dx? Do people at home good or no?
Good.
Good.
Great? Did they say great? Great. Great. All right. What's our next dy dx? 2.4 plus 0.92 ought to be? What? 3.32. Sounds good to me. Which makes our delta y 0.664. Everybody good there? We're now at 2.6. And now an even more annoying number. I don't know, what does that come out to? 1.584. Yeah. Okay. And dy dx then becomes 4.184. And dy dx becomes 0.8368. All right, I hope. Everybody at home good with those?
Yes.
Yep.
Okay. Next value then should be 2.8, and then whatever 1.584 plus 0.8368 is. 2.4208. And add those together, we should get 5.220. And there's a 0.2 still. Multiply that by 0.2. What do we get? 1.04416. And now we are at our last value, which should give us 3, comma. And now we got 3.46496. And that is Euler's method. There's not really all that much to it. Good or no? You guys good here? Derek, you all right? Yeah? Okay. No. There's no. Question was, is there a way to know how accurate that is? The answer is no. So if you guys can hear Noah asking. Y'all good at home? Any questions on that?
I have one. So you said on the AP test that they might only have you do a few because the addition might get irritating.
Yes.
Does that mean they'd make us do this without a calculator?
That is correct. Generally, this is in the non-calculator free response questions. Yep.
So they'd make us do the decimal multiplication without a calculator?
That is correct.
Okay.
Yes. I mean, but like I said, it's probably going to be, find f of 3, give an f of 2, but use a step of 0.5. So the arithmetic won't be that bad after this 2 steps.
Okay, thank you.
But yeah, you will need to be able to do some basic decimal multiplication on your own.
But they wouldn't make us do 5.2208 times 0.2, right?
I have never seen one that is got this bad of arithmetic on the AP test.
Okay. Okay.
No promises, but never seen it. All right, let's let you guys work through this one together, or on your own. I mean, not together, together on your own, without me, without my assistance. You guys do this one. Sound good? And then we'll make sure that it all looks good, and that'll be Euler's method. That'll literally be all we do with Euler's method. And we might start logistic growth, or it might just be like, all right, we're done because we're running out of time. Okay, just to practice, make sure you got it. Ready, go. Okay, we all good now? Ready-ish? Ready enough? Yeah. Okay. Help me with my arithmetic here because I have an old and feeble mind, apparently. So let's make sure we're doing this right. 2, 3, 1, -0.1, and -0.1. Everybody agree with the first one there? So our first step here should be now 1.9 and then 2.9. And we got 2x minus y. That should just be a 0.9. Yep. A -0.1 here should make this a -0.0. We all agree with that? Next step should be 1.8 then and 2.81. And we got 3.6 minus 2.81 should be, what is that, 0.79? And then this should be a -0.079. Everybody good so far? You guys at home good? All right. And then what does that give us when we subtract that? Now you said, what does that come up? 2.731. Everybody agree with that? Cool. Then what do we get for our dy dx? 0.669. -0.1 again makes that a -0.0669. Everybody still good? 1.6 and 2.6641. And then our next dy dx should be what? 5359. The -0.1. That sound good to everybody? Giving us -0.05359. And our value then at x equals 1.5 comes out to do what? 2.61051. Everybody in class here good? Y'all got that? Y'all at home got that? That good?
Yeah.
All right. That is Euler's method. Easy. True? And in fact, it will be easier than what we just did on the AP test. That's all we have to say about Euler's method. Okay. We don't have much time, but we have enough time for us to at least basically start on what logistic growth is. So we're going to take 2 seconds to do that. So this problem right here is what you traditionally look at. Oh, you can't see it. I didn't share the new screen, did I? This is what you might traditionally get when you're in, like, 6th grade and somebody first tells you about exponential growth and they're like, all right, we're going to have 2 rabbits in the class, because this is what they talk about in 6th grade. Like, we're going to have 2 rabbits in the classroom, and all of a sudden after a year, at the end of the year, we're going to have 50 rabbits. And then they'll have like the whole sex ed discussion about how we got 50 rabbits from just the 2 in a year. And then the next year, the class will be like, we went from 50 rabbits to a lot more rabbits. So I want to know, how many rabbits do I have? But this is exponential growth. How many rabbits do I have after 5 years? Using exponential growth, the formula should be y equals y naught e to the kt, right? And we know that after 1 year, we went from 2 rabbits to 50 rabbits. That should tell us what k is, right? K equals the natural log of 25. True? So after 5 years, not 50 years. After 5 years, we should have the final amount of rabbits equals my initial amount times e to the 5 natural log of 25. And how many rabbits do we have after 5 years? Calculator, people. $19,531,250. And we recognize, number one, that this is not sustainable for my classroom, because even with only 4 students in the classroom, I don't think we can fit 19,531,250 rabbits in here. And if we did, they would either have to become cannibalistic to survive because there's not enough food for them. And that's just not how population growth really works. Do we all agree with that? Okay. So back when you were in 6th grade and you modeled population growth using exponential growth or something like this, it just doesn't make any sense. So in the real world, generally, a population will increase at what we call a logistic growth function, more active. And a logistic growth equation, rather than our exponential, right? Our exponential was dy dt equals k times y. Our logistic growth, which will start off looking, I'm going to ask this on my drawing now. It will start off looking exponential, but then it will level off. And this is logistic growth. It looks like this. Rather than exponential growth, right? Exponential looks like crazy numbers of rabbits. Right? We don't have 19 million rabbits after 5 years. We have quick growth of the rabbits, and then all of a sudden there's not enough food for them, or there's no space for them in the classroom, and they start to narrow. Right? They grow very quickly, but then they narrow. And that's logistic growth, and that's what we're going to deal with starting tomorrow. And logistic growth will follow this differential equation. dp dt equals kp times m minus p. So the rate of change of the population, where p is the population, is equal to some constant times the population times some other constant m minus the population, the amount of the population. And this m value that we're going to talk about, and we'll mention this again tomorrow, this m value is called the carrying capacity. And the carrying capacity is the maximum value that this population could hit. We will have a horizontal asymptote basically up there at m. M is the largest value for this population. We start talking about logistics. And that's all I'm going to really say about it today. Tomorrow, we're going to go through and we're going to solve this general logistic growth equation to come up with the formula for the for logistic growth or any situation that is given to you, and we'll talk about some of the basics of it. It shouldn't take, I mean, we'll be done by the end of the period, and you'll have a formula for it, and it should be good. Everybody good with the idea of what it's going to be and what it's going to look like? Y'all good here? Y'all good at home? I think that should be good for today. Those of you in Zoom, if you